So there's a formula for that, right? There's a cubed minus b cubed becomes a minus b, a squared plus ab plus b squared. There's also a sum of cubes formula, which is really similar. I think we might have even done one of those before. This is probably not going to be on there because you do have to know this formula, but because I don't know, this is just like it's out of the usual comfort zone for most students. But in your problem, the a is the sine t and the b is the cosine t. Is that clear for the numerator?
Yeah.
Okay. So we're going to break it apart. The numerator becomes sine t minus cosine t. That's the a minus b. Sine squared t, that's the a squared. Then you smush them together, sine t cosine t, plus you square the last cosine squared t. And hopefully it's clear why the squared is there. So we now have sine t minus cosine t on the bottom, and those cancel. Those go away. Which is really nice. But we're not quite there because you can see the answer is not what we have written. It's the 1 plus sine t cosine t. Bring that down. Sine squared t, I'm going to reorder it, plus cosine squared t plus sine t cosine t. And then you're supposed to recognize that this right here on the left is an identity. It's one of the Pythagorean identities. Do you remember what this equals?
1.
1. And that's what we're looking for, because our final answer is 1 plus sine t cosine t. Is that okay?
Yeah, that one is pretty straightforward, actually.
Yeah, no, not too bad. Let's do 72 next because it's kind of like the one we just did, and then we'll come back and deal with 70. So 72, let me snip this in. 72 here, like the bottom is difference of squares, but so is the top. And the top has got a higher exponent, so you probably work on the top first. It's the a squared minus b squared, which ends up being a minus b, a plus b. And so it's not squared though, but if you think of a as sine squared alpha as being squared, and b as being cosine squared alpha being squared, then you get back to the power of 4s. So your a is the part inside parentheses, b is the part inside parentheses, like that. So this one could be, I guess it could be a little bit confusing, but the way it's broken apart, if you understand this, is the top becomes sine squared alpha minus cosine squared alpha. That's the a minus b. Sine squared alpha plus cosine squared alpha, a plus b. And then you're dividing by, and that's where you almost have to look ahead to know, oh, I'm going to divide by the same thing I have on the top. So again, just kind of like the last one, these cancel. And then hopefully you recognize that sine squared alpha plus cosine squared alpha ends up being 1 by the identity.
I'm sorry, how did you split it into sine squared alpha minus cosine squared alpha again?
That's the whole difference of squares. So the numerator is a power 4 minus a power 4. And that's just a variation on the difference of squares, where the thing inside parentheses is squared. So when you square a square, you get back to a 4.
Oh,
square,
okay.
you get back to a 4. Yeah. All right. So 70, look at 70. Yeah, so with 70, you've got like both sides really have issues. On the right side, you got a 1 plus sine alpha on the bottom. We know from past experience you generally multiply by the conjugate. Okay. But it's really awkward because like when you do that, you're going to get something on the bottom, something on the top. Like this is still going to be a fraction when you start messing around with it. On the left, you are going to have to write this out as two binomials, secant alpha minus tangent alpha, do that for you here, times secant alpha minus tangent alpha. And you're not going to get a fraction from this. So this one lends itself to like, you have to manipulate both sides. And I guess I would probably tell you to work on the right first, but know that at some point you're going to have to do this on the left to get where you have something that you can try to get to be the same. Okay. So the top is going to be 1. We need to FOIL the top. I guess we need to FOIL the top and the bottom here on the right. So, again, not great, but that's what it is. So 1 times 1 is 1. And then you got minus sine alpha plus sine squared alpha. And then on the bottom, when you FOIL, you get 1 minus sine alpha plus sine alpha minus sine squared alpha. And what you notice, hopefully, is that the O and the I, the outer and the inner, cancel. So on the top, just rewriting a little bit, you get 1 plus sine squared alpha minus 2 sine alpha, like that. And then on the bottom here, you have a 1 minus sine squared alpha, like that. Again, it's not much better, but we had to do something. We had to take a step here. The 1 minus sine squared alpha, that is going to become a cosine squared alpha because of the identity, that trig identity. Sine squared alpha plus cosine squared alpha equals 1. So again, that doesn't really help, but it does get one thing on the bottom instead of 2, like that. And that's where we probably need to go work a little bit on the left and hope that we get something useful. On the right here, I can tell you we're probably going to divide each of these by the cosine squared.
How do you know that you need to simplify both sides instead of just one side?
You really don't know unless you've done this before. Like there's no way to make a fraction into a square as is a square into a fraction. So generally you only work on one side when like one of the sides is nice, but if they're both reasonably complex, you have to work on them both. There's no rule. There's no like, oh, here, this always works, unfortunately. And by the way, I don't really know how this one works. I know we've got to probably work on both sides. If I've done this before, it's been so long, I couldn't tell you. So I just taking a guess and hopefully it works out. And they call that a swag in you can look that up later. So the secant times secant is secant squared on the left. And then you get minus secant tangent minus secant alpha tangent alpha plus tangent squared alpha, like that. So you get secant squared alpha plus tangent squared alpha minus 2 secant alpha tangent alpha. So this is where you know, I'm starting to see like, oh, there's some good stuff here because do you see down here we've got a minus 2.
Yeah.
We've got a 1 over cosine squared, that's kind of a secant squared. Sine squared over cosine squared is kind of a tangent squared, or it is. So I'm feeling pretty good right now. So now I'm going to work on the right side. I'm going to go back to the right side and again, write each of these over the cosine squared alpha. And then for this last one, it's going to be cosine alpha instead of the cosine squared. And then I'll bring this one down. Okay, so again, just working on the right now. Secant squared alpha, tangent squared alpha, minus 2 tangent alpha, and then there's really a 1 above the cosine secant alpha, and now we have it. Now, you know, full disclosure, you actually did not need to work on the left side now that we've kind of seen this one work all the way through, because you could actually, if you rewrite this one, you could recognize that this is a perfect squared trinomial, secant alpha plus tangent alpha, I'm sorry, minus tangent alpha squared. Like that. That's just factoring this as a perfect square trinomial. You know, would you have seen that? I doubt it. You gotta, you know, that's why you don't have to work on both sides, but sometimes it helps to do that, especially if they're both kind of reasonably complicated. Like 80 is a one. If we look ahead to 80 is when we'll work on both sides of this.
So the other thing that I don't get is, so how do you know exactly which direction to go to? Because like you can solve these problems in so many different ways. Like, how do you know that instead of changing the tangent into sine and cosine, you change it to like 1 over cotangent? It's like there's so many different
Yeah.
ways the problem can go. How do you know like which way is the right way?
Yeah, your question's a good one because you're right. What I think you're leading to is like, well, like how am I supposed to know how to do these? And it's hard. There's no simple answer. Proofs are like that. And I'm sorry that's not a great answer, but proofs are like that in math. I don't like proofs very much personally. So I mean, I get what you're saying. You know, you're used to a recipe. You're used to like do this, do that, and then you get the answer. That's not the case here. And that's not a good answer, but that is unfortunately the way it is. I wish I had more hope or optimism. Um, once you do these, you don't see these again in math. Okay, like you don't have another trig proofs thing in a traditional track in college. But I'm sorry. I wish I mean, I liken it to, I don't know, like there's things in your life where you're like, all right, I'm going to spend some time over here and then I'm going to spend some time over here on the right. And then like eventually it kind of all works out.
Mhm.
I mean, I don't have a good example of that off the top of my head, but, you know, things kind of, I don't know, building, if you ever build stuff like a puzzle, maybe it's like a puzzle, you know, you work on the border, work on something else, and all of a sudden it comes together, you know, way down here. You're like, oh, that's cool. There's not a great, but there's no formal like always do this and this works.
Yeah.
There's just guidelines. Has your teacher given you an explanation for that?
No, no.
Okay.
But he basically like admitted to us that this is so difficult that he wants us to know the process rather than actually like solve them on the
Yes.
fly.
Yeah. So you've got your teacher's got some experience there, because if I were teaching this, I would give you like, I'd have, give you all the problems here and say, on the exam, I'm going to give you, one of this grouping, one of this grouping, one of this grouping, and you spend enough time practicing them, you'll be able to put something down and get a decent score. It's just not, there's nothing practical here. I mean, there's no, no usefulness, but yeah, I mean, that's all I've got to say on this. Won't be the last time you
Yeah.
see something like this. I mean, this is, this sometimes just something. So, all right. So, few things here. You might see, I mean, like you got fractions on the left. So like you might think, well, let me combine the fractions, do some common denominator stuff. On the right, I see that there's a cosine squared that goes into both of these, so I'm tempted to factor that out. But beyond that, I'm not sure. Okay, so this again feels like one of those where you might have to work on both sides. I'm going to choose the right-hand side to work on just because it's got the higher power. And maybe there's something to that. I'm reading a new book, and it's a business book, and it talks about the idea that sometimes you just try something without having all the justifications for doing it. Because if you take action, you learn something. And you learn more through, and I hate saying this, failures than you do successes. So as long as you've got a reason, you do it. That way you feel like you have some justification for it. And it doesn't have to be in math, it could be for anything in life. All right, so
Yeah.
that's enough on that. Factor out a cosine squared from both. Now, just looking at the right side, does anything jump out to you?
Um, cosine squared.
So let me help here. This should jump out at you right here.
What wouldn't that equal sine or sine
Sine,
squared?
yes, yes.
Yeah.
Okay. Now, kind of another thing here, since they're multiplying, and this kind of answers your questions a little bit more, is it is a lot like a puzzle. Like sometimes you're like, well, let me see if like, does this work out any better? Like you sort of work on it and you're like, all right, well, it's either this or it's this. Now let me go to the other side and see if I can find something that matches. So because we know on the left it's kind of the same, it's just it's plus. So let's work on that and see if we can make it a product. And we do that by making a common denominator. So 1 over cosine squared t, 1 over sine squared t. We're going to multiply them both by the other one. So it's cosine squared t sine squared t plus cosine squared t up top over cosine squared t sine squared t on the bottom. Does anything on the left now jump out at you?
The top equals 1.
Yeah, and that's good because then it becomes 1 over cosine squared t sine squared t. And so this is where you got to recognize that these are the same. And you've got it now. Any questions on that or any?
No, that was pretty easy actually.
Okay. So like the way the brain works is once someone asks you a question or probes you about something, you like continue to think about it in great detail. There are some guidelines like we've talked about, like you convert everything to sine and cosine. Whenever you see squares, that's your Pythagorean identities. You almost always multiply 1 plus sine, cosine, tangent, plus minus secant, cosecant, cotangent by the conjugate. So you almost always multiply by the other one, the 1 minus plus now of that list. You generally convert sums to products. You generally work on higher exponents. Does your book not have sort of this list in there, like 5 or 6 rules?
No.
Okay.
They didn't even give us the Pythag identities. You just kind of expected us to know that.
Yeah. Well, let me see here because I've got this book out and maybe there are. I mean, it's like a cheat sheet, right? It's like here's a few strategies. Wow, this is awful. They actually don't give you anything in here. Okay. So this is kind of the list we've been working on, but there's so many other things, like you have to know all your factoring and you have to know your foiling. But this, this is kind of a list to think about. All right, let's go back and look at we did 70. Let's go look at 76 together. Now, are you discouraged when you go down the wrong road, or does that motivate you?
Honestly, I get discouraged.
Yeah. Okay. That's why you're where you're at right now. I fully expected that answer because these are discouraging. Proofs are discouraging. They if you can't lead yourself to the right path, you're like just totally over it. We're going to work on the left side here, this one. And the the problem, like you just mentioned, is like, well, what do I even do? And if we look at this list, you can convert everything to sine and cosine. There are no squares. You do have a 1 minus tangent, 1 minus cotangent. So number 3 is in play. You have a sum that's going to go to a product. Number 4 is in play. So there's basically 3 things in play, 1, 3, and 4 on this one. Again, like I don't know how to tell you that, like from experience, I know we're going to multiply by the conjugate on these. But like I don't know how this works. Like I don't know that it's going to work out. But I'm pretty sure it will because this is this style. So I don't know if that gives you less hope or more hope, but it's not like the graphing rationals where I can say, oh, here's the recipe, this works every time. So we'll multiply by 1 plus tangent theta. Are you planning on taking calculus in college?
Most likely, yeah.
Next year? Next year, okay. Where are you going to school, by the way, if you know?
I'm going to community college or Pima.
Pima, cool. So if you take their calculus class, there's some stuff there that, again, it's kind of like this where you just don't know until you've been told, like we're not expecting you to invent anything new. Someone needs to tell you this. But the 1 minuses, 1 pluses, those are good indicators that you're going to multiply by the reciprocal or by the conjugate. So on the bottoms, like it's really good if you can get to a point where you recognize this is difference of squares. Do you know what I mean by that, or is that still like this is a
Uh,
minus b, a plus b?
so whenever you see 1 minus and then 1 plus, then it's different to squares.
Yeah, and it saves you time, ton of time, because if you don't have to FOIL, if you can just write 1 minus tangent squared theta, and that's what I hear a little bit of is like if you just had a shortcut to do these, you'd be more willing to try. But the algebra is so tedious. And I'm not, I don't disagree. But the same thing with the one on the right here becomes 1 minus cotangent squared theta. So in some ways we're very similar. Like when I was a student, I would probably have foiled this, but eventually I just was like, I'm so tired of doing this. I'm gonna just finally accept that it's this. And then it makes it a lot faster. Like, do you know that when you pour a glass of water, you don't aim for the cup, you just do it?
Yeah.
I mean, that's what I'm trying to get, that's what we're trying to get you to do here is like, be like, just believe that you can do it and not have to aim and make sure it's kind of right. Like, oh yeah, they cancel. I mean, there's nothing more frustrating than being like, I should have known that. I should have just went straight to it. All right, in the numerator, we're not going to do anything yet, which I think is also maybe not clear why, but it has to do with what's going to happen in the bottom. Both of these on the bottom are identities, right? 1 minus tangent squared, 1 minus cotangent squared. Do you happen to have those up? If not, I can grab them as well.
Wait, can you repeat that? Sorry.
These are identities on the bottom now. And I was just asking if you had them in front of you.
Yeah, let me check.
I got it. I'm snipping them in. And is my audio coming in clear?
Oh yeah, it is. Oh
Okay.
yeah, I have them in front of me.
Okay. So like this is another, like this goes on this list up here, which kind of the squares. It's like you need, and it's not just the squares, it's the 1 minus the squares that you have to know. Like you have to immediately know that cotangent squared is cosecant squared minus 1, for example, and tangent squared is secant squared minus 1. So like just to be clear, like on the one on the left here, tangent squared is really secant squared minus 1. And that's from this one right here. Is that clear? Like you subtract the 1 from both sides and substitute in.
Yeah.
All right. But now that I'm looking at this doesn't look that great. Because because these don't cancel, it becomes 1 plus plus, and that's what I was hoping for. So I may have taken you down the wrong path here. We may have wanted to do something different. We may have wanted to do the sine and cosine stuff first. I'm sure that's frustrating. Because the bottom doesn't get better, and they're not a common bottom either. So I think that was a mistake. So we're gonna have to restart this problem. And go down the road of sine and cosine. So the cotangent is cosine theta over sine theta. 1 minus sine theta over cosine theta. And then tangent, again, sine theta over cosine theta. 1 minus cosine theta over sine theta minus 1. So what I'm seeing here is on both bottoms, we can make them into common denominators. So we're gonna make the left cosine theta over sine theta, and this one on the right sine theta over sine theta. So again, if you can just minimize how much you write, it's cosine theta over cosine theta minus sine theta over cosine theta plus sine theta over sine theta minus cosine theta over sine theta. And the tops are the same. You should write them. I'm gonna skip that for now. So the bottom becomes cosine theta minus sine theta over cosine theta, sine theta minus cosine theta over sine theta. So again, just, a little bit more work to do here. Okay. And then if we multiply by the reciprocal, so like this cosine theta is going to end up coming into the numerator up here. Same thing with this one on the right. It's by multiplying by the reciprocal top and bottom. So we do need that top now. So let me snip that in. That one, that didn't work out real well. Cosine theta over sine theta over cosine theta. So what I'm trying to show you here, and there's a lot of stuff here, is that the when you multiply by the reciprocal, cosine theta over cosine theta minus sine theta, cosine theta over cosine theta minus sine theta, you can see that everything on the bottom cancels, and then the thing that was in the bottom goes to the numerator. So you end up getting cosine squared theta over sine theta times cosine theta minus sine theta. And then same thing over here on the right, sine theta minus cosine theta, sine theta minus cosine theta. All right, so you get sine squared theta over cosine theta, sine theta minus cosine theta, like that, -1. Still not much better, but you can maybe see like there's something going to happen here with this that might be good. So we'll get there. There is some imbalance. There's a sine on the outside, a cosine on the outside, and there's also a negative. These are in the wrong order in here, so we'll deal with one thing at a time. So the first thing is, let's deal with this negative on the right. So if you pull the negative out, it flips these, and so it changes this to sine squared theta over cosine theta, and then switch the order, cosine theta minus sine theta. All right, and then again, you kind of got this weird imbalance, but we're going to then get the common denominator of being a sine theta and a cosine theta, and then the cosine theta minus sine theta. So the one on the left here, we're going to multiply by cosine theta, and the one on the right here, sine theta, and now we'll get the balance that we want. So cosine cubed theta minus sine cubed theta over sine theta cosine theta times cosine theta minus sine theta -1, like this. So it's possible I've gone to the wrong place here, because none of this is working out nicely, but we would keep going here. So the top is difference of cubes, which will cancel with this one here, which is good. So top becomes cosine theta minus sine theta, and then it's cosine squared plus cosine theta sine theta plus sine squared theta, all over, reordering it, cosine theta minus sine theta. You can see those cancel, and then sine theta cosine theta here. And believe it or not, it is getting better. It doesn't look like it, but it finally did here, because this pops out, those cancel. In here, cosine squared plus sine squared is 1. So you're left with 1 plus cosine theta sine theta over sine theta cosine theta. Still have this -1 here. And then you divide each of these. So 1 over sine theta cosine theta plus cosine theta sine theta over sine theta cosine theta -1. So then the ones the ones in the middle here become this one becomes 1 minus 1. So see how those cancel. It's kind of nice. And then this one is 1 over sine theta, 1 over cosine theta. So cosecant theta, secant theta. So that one's probably not going to be on there for all that, because it's just I mean, how do you even know? There might have been a shortcut. I mean, this is one of those I'd love to see what the textbook solution is, because you could see I went the wrong way to start. But you know, when you see the PDF, this is at least 2 pages of work. All right, 78 is probably the one we have not done. Hopefully this doesn't take the full 10 minutes, but it might. Sometimes they're deceptive, like, you know, they don't look like they're gonna do that, but okay, so just trying to, you know, I sort of like say, okay, sine tangent is sine over cosine, so you're gonna have a sine squared over cosine, and here you're gonna have a cosine squared over a sine. So I'm gonna start with that sine beta plus, and then when I multiply this in, you know, sine beta over cosine beta plus cosine beta plus cosine beta over sine beta, like that. So the thing that jumps out to me here is we've got a sine beta plus a cosine beta, and then sine squared beta over cosine beta plus cosine squared beta over sine beta. Now, because the last one was difference of cubes, like I kind of see that we could be heading that direction here, because you can see that if you multiply to make a common denominator here, you're going to get cubes. You're going to get sine beta, cosine beta, cosine beta. So we got sine beta plus cosine beta, sine cubed beta plus cosine cubed beta over cosine beta, sine beta, like that. So now that, like, because we've done a couple of these sum and difference of cubes, the top one is going to cancel with this. You're going to see that cancellation in there. So that's good. That's good news. But like, I don't know. I still don't know how this is going to work. Honestly, like, I don't know. But like, you know, I don't sit around like working on these types of problems. These aren't interesting to me either. So I don't, I just would encourage you to try what we've been trying on the exams. Plus, having
Yeah.
all of these in your notes might do something. It might help, you know, okay, I've done a few of these. Okay, so the thing that I'm noticing here, just like all the other sum and difference of cubes, you get that sine squared, cosine squared, that becomes 1. But yeah, man, I mean, this is not great. So you get sine beta plus cosine beta, 1 plus sine beta, cosine beta, like that. And then over this. So, yeah, I'm trying to avoid having, I mean, we do at some point need to divide everything, but is there really nothing else that happens here? I mean, I don't want to foil this one on the top right, but that's kind of where it's leading. At some point, we're gonna have to make a common denominator, but holding off on that. Yeah, nothing greater. So I guess I'm gonna foil sine beta plus sine squared beta cosine beta plus sine beta cosine squared beta plus cosine beta. And then each of these is going to be over cosine beta sine beta. Okay. And we still have this stuff to bring down as well, which we'll do in a moment. So the sine beta over sine beta, you get 1 over cosine beta. The good news is that's a secant, and we do want that, plus a sine. Wait, I missed a sign. I'm sorry. This is negative. That's why this isn't working. That's why this isn't working. Okay. Okay, that's really bad. I'll give you those two formulas again, but so the sum of cubes has a negative here. The difference of cubes has a plus here, but that propagates through a bunch of this. So that would have been, this one would have been negative. And then this last one, this next one would have been negative. And because I did that, and then I did that, which I don't know why, and then I did this one, and then this one. Yeah, okay. I foiled this oddly, but it'll sort out. So this becomes sine beta, but it's negative, and that's really good because you can see we've got one on the left to bring down sine beta. And then you get your next one here ends up being a cosine beta, and that's good. And then this ended up being 1 over sine beta, which is cosecant beta. So cancellations here galore. Those cancel, those cancel, those cancel, and you're left with secant beta plus cosecant beta. If you dozed off in the middle of that, I understand. But
Yeah, just a lot.
this is these, especially for the later ones, you do have to know. I messed this up because I didn't write it down. I almost always write the formulas down as I'm using them. But the main difference between sum and difference of cubes is the signage. They match here and then they differ here. You can see the negative goes to a positive, the positive goes to a negative. And that could be all the difference with that. So I don't know. Give me some feedback. I mean, if you need to vent, I mean, we should spend 3 minutes and you can just sort of vent and say how awful this is.
I mean, I already kind of know how awful this is, but I'm in this class. I have to do it.
Yeah, and I'm looking, let me just look at my book here and see if there's any other kinds of these strategies to doing these. Sometimes there's more than one. I mean, this is like the common denominator is kind of a big one. And you see in these problems. Foiling, factoring, we talked about. Using identities, we talked about. Yeah. So what's your plan? We got another lesson tomorrow. What's the game plan for that? I think we do have another lesson tomorrow. Is that right?
Yeah, we do.
Okay. What's kind of your game plan for that?
Well, I kind of know the types of questions that will be on the